Yeah, let's start today's discussion. Today is the today is week 5 problem solving session of fundamentals of power electronics. And in this week, the topic of discussion is the protection circuits for limiting the inrush current in a diode bridge rectifier with capacitive filter, and then a little bit about three-phase diode bridge rectifier, and lastly, the concept of power factor. So before starting today's discussion, in last week we were discussing the design of a diode bridge rectifier with capacitive filter, if you remember, for single phase rectifiers. So the last question, the which asked, which was a design problem, you need to design a diode bridge rectifier. So that was not complete. Today I shall explain that problem once more because I couldn't complete it last day. Then I shall start today's discussion. Okay. So the problem was like this. Uh, so while you will be asked to design a diode bridge rectifier, these parameters will be given. First, the AC mains voltage. This is the standard AC mains voltage, 230 volt 50 hertz with a tolerance of plus minus 5%. So this 230 volt is the nominal value. It can be, it can go higher than this and lower than this, and that range is given plus minus 5%. Another data is given, which is output power. This is the power that will be delivered to the load, that should be delivered to the load, 100 watt. Next data is maximum source current. So the current that will be drawn from the input source, the maximum value of that current is 1 ampere. What else? Another thing is maximum ripple across the capacitor. So even though we have given a capacitive filter, but still voltage will not be perfectly DC. There will be some small ripple in the voltage, and that ripple is 15.45 volt. So all this data will be given to you. Using all this data, you need to design the diode bridge rectifier, different components. You will have to find the value of the capacitance, the which you will use as the filter. You need to find the RMS and average current of flowing through the diode so that you can choose the diode. Right, all these things you need to find so that you can select the components, the passive components as well as the semiconductor devices, which is diode in this case. Is it okay? So this is a standard design formula. Okay. Uh, Next is here I have shown. So the tolerance was given to the range of the source voltage. I have calculated the maximum peak of the input voltage and the minimum peak of the input voltage. So while when RMS value is given to us, the peak value should be RMS times root 2. Here I have multiplied 1.05 because the range was plus minus 5%. So 1.05, this will give us the maximum peak, and 0.95 times 230 root 2, this will give us the minimum peak. And here there are certain angles are there in this diagram. So this is the angle alpha from which the charging of the capacitor starts. So from this and the duration is beta. So in this portion the capacitor gets charged, and after this, when the value already reached to peak, after from this point onwards the capacitor will discharge. That we already discussed last day. Uh, right, like this. So this is the steady state waveform. This is the steady state waveform of the output voltage, this bold black one. And this one is this dotted line is the voltage if this is the voltage which we will get if there is no capacitive voltage. That also we saw that if there is no filter, we will get this kind of voltage. Only it is simply the flipped AC voltage. For AC voltage, the input voltage is like this, bipolar, and after rectification, the negative portion just gets flipped, and we get this kind of voltage. Right. So once we have these values, Vm1 is the peak value. So we have two peak values, and VM2, how can we get? We can get the VM2 value by subtracting the ripple value, because this is the ripple that I told you. The difference of this maximum and minimum value is the voltage ripple. And the ripple value is already given to us. If we subtract the ripple value from the maximum value, we can get this minimum value, this point basically, which has been denoted by VM2. And this Vm2 is nothing but Vm1 sine alpha. As this is a sine wave, right? And this angle is alpha. So if we do Vm1, this is the peak value. So Vm1 sine alpha gives us Vm2. That's what I have written here. And delta V is given. So from this we can get the value of alpha. So this angle is alpha from here to here, but beta is the duration when the capacitor is charged. This is the duration from this point to this point. Okay. I have calculated in degree as well as in radian. And now we can calculate two sets of value because we have two sets of peak voltage. So corresponding to those voltages, we can have M1 max, M2 max, and VO. Right, VO max. So this is basically half of VM1 plus VM2. And for this minimum peak value also, we can get all these values. We can have another voltage of output voltage. Okay. We have two sets of values. Now what will we do? We will calculate the capacitor value. And last day we saw one numerical problem where they asked the energy lost during the discharging period. Why energy is lost? Because the capacitor gets discharged. The capacitor provides the load current in this period. No current is drawn from the source. The capacitor provides the load current during this period from this point to this point. So some energy from the capacitor is lost, and that lost energy is half C Vm1 square minus Vm2 square, because Vm1 is the initial voltage and Vm2 is the final voltage at this point. So this is equal to power times the power multiplied by the time duration. What is the time duration? This duration is pi by 2 plus alpha. This duration, the discharging duration. Why? Because this angle is pi plus alpha and this angle is pi by 2, because this is the angle at which it reaches the peak. So this duration is pi by alpha minus pi by 2. Pi plus alpha minus pi by 2, which gives us pi by 2 plus alpha. And if we divide it by omega, we will get the time duration. And we know power multiplied by time gives us energy. So that's why I have written uh, in this way. Here, if you just uh, extend it, this is Vm1 plus Vm2 and Vm1 minus Vm2, this portion. And half Vm1 plus Vm2 gives us V0, right? The output voltage. And Vm1 minus Vm2 is nothing but the voltage ripple. So voltage ripple we know, output voltage we also know, P we know from the data given to us. We have calculated the value of alpha, and omega is also known to us. All these quantities are known. From this we can calculate the value of C. Now one question is which set of value we should take, because we calculated two sets of values here. Which set to take? I have taken the minimum, this one. Why? Because if you calculate, see, taking both these values, you will see that taking this minimum set of values, you will get a higher value of C. And whenever we are designing something, we should always take the worst case scenario. So whichever set of values gives us the higher value of capacitance, that value we shall take. That's why I have taken this set of values. This VM1, this VM2, and this V0. And I have replaced the values here. And if you calculate this, you will get C equal to 193 microfarad. Is this clear to everybody? Okay. So this is the capacitance calculation part. Next, we need to decide, we need to calculate the diode parameters so that we can choose a diode for the application. Another thing, we can also actually, while we will choose the capacitor, there is the voltage rating is one thing. Another thing we will require is the RMS current value, because uh, the current uh, okay, the picture is not here. So basically some current flows through the capacitor, some AC current, and we need to know the RMS of that current so that we can choose the capacitor. The capacitor should be able to withstand that current. That's why we will also calculate the RMS current. What is the RMS current? So this is the current that goes, I don't have the picture today, but yeah, last day we saw that the current entering the load portion, the current gets divided into the capacitor and rest of the current goes to the load, right? So this is the current shape, because only this is the current shape and this is the source current. So this is the current that that is getting drawn from the input source. Okay. Now, this is the, suppose this is the maximum value Im. So from this Im, if we just subtract the average, the load current, because the capacitor current is nothing but the subtraction of the total current minus the load current. So that's why I have subtracted I naught and I have multiplied the duration. What is the duration? So this is the duration. Beta is the duration when the capacitor gets charged, divided by the total duration, which is pi. So this is the duration, and when the capacitor is discharging, the load current is equal to the capacitor current, right? Because capacitor is only providing the load current. So that's why I have written I naught. And here the duration is pi minus beta by pi. So this duration is pi, pi minus, so this is the total duration pi. If we subtract beta from it, so that will be the discharging duration, right? So that's how I have calculated the RMS current. And that comes out to be 0.37 ampere in this case. So whenever you will choose the capacitor, its RMS current rating should be always more than this. And after that, I have calculated the diode average current and RMS current. Diode average current is nothing but beta by 2 pi, because two diodes conduct during the positive half cycle and the rest of the two diodes conduct during the negative half cycle. So in a complete cycle, each diode conducts for beta duration and the total duration is 2 pi. So the average current becomes beta by 2 pi and RMS current is the square root of this. So these are the values. And peak inverse voltage. This is also another important parameter for choosing the diode. What should be the maximum amount of voltage the diode should withstand? That comes out to be root 2 times Vrms into 1.05, because again we have one tolerance of the grid voltage. So I have multiplied 1.05 and this is 341 volt. So the peak inverse voltage rating of the diode that you will choose, that should be more than this value whenever you will choose the diode for your circuit. Okay, so that's how you can design one diode bridge rectifier. Now I shall start today's discussion. Today's this the first I will discuss the different protection circuits that are used for limiting the inrush current. Now, what is the inrush current? While discussing yesterday, we told that see, whenever you were paralleling one voltage source with another voltage source, so capacitor is kind of, it stores charge, right? If it stores charge, and that's why some voltage comes across this capacitor. And for a capacitor, the voltage doesn't change very drastically. It retains the voltage. That is the property of capacitor, and that's why we use capacitive filter, so that the fluctuation in the output voltage reduces. Now the problem arises because when it has reached steady state, it is okay. But when you are starting the circuit, suppose this is a switch, and whenever you are closing the switch, the circuit is closed, and the current will be drawn from the source. Now, initially there is no voltage across the capacitor. Initially, when you are just starting the circuit, just before closing the switch, there is no voltage across the capacitor. But the AC, some voltage is here. This is the AC voltage, the grid voltage. Some voltage is there. So you are paralleling this capacitor with this source here. So here basically the diodes will act as closed switches. So I have not shown the diodes. So the equivalent circuit is one AC voltage source along in parallel with a capacitor. Initially there is no voltage because there is no stored charge in the capacitor. So initially it will draw a huge amount of current. What will be that current? The initial current will be Vi, this is the source voltage, minus Vc. Initially this is 0, this quantity is 0, divided by Z. Z is the impedance of the circuit. And this impedance is what? The source impedance, and some very small amount of forward resistance that is offered by these diodes, right? So this impedance is very, very small. As a result, you will get a huge amount of current initially. Okay. And this current may exceed the diode ratings. If the current exceeds the diode ratings, the diode will get damaged. And before even reaching steady state, your circuit will be bad. Right. So it is very important to limit this inrush current. And there are some protection circuits that we need to employ so that this current can be limited to a safe value, where these devices can withstand this current. Is this fine? Okay. Sorry, I didn't hear. Did you ask anything?
Is this the that voltage of diode, knee voltage?
Your voice is not clear. Just repeat once. Or you can text also. You can type the question. Uh, who asked the question? Just repeat once. I didn't hear it. Uh,
Hello.
हाँ, tell.
I was saying that is this said the knee voltage of the diode?
No, this is not a voltage. Z is the impedance of the circuit. So whenever you are calculating a current, what is current? Voltage divided by some impedance. That impedance of the circuit. What is the impedance? The impedance, the source will offer some impedance. This source, there will be some impedance associated with the source. And actually, this idea, we assume that these diodes are ideal, but actually, practically these diodes will offer some forward resistance. Whenever the current is flowing through these diodes to charge this capacitor, there will be some forward resistance of this diode. So that will also contribute to this impedance. But even if like this complete impedance of the circuit, these diodes, they contribute to a very small amount of impedance, which is not sufficient to limit this inrush current. That's what I was saying, that the voltage is a like sufficient amount of voltage, and initially the capacitor has not stored any charge, so there is no voltage across this capacitor. So vc is this just uh, vc is this voltage across this capacitor. So initially this is zero because there is no voltage across the capacitor when you are starting the circuit. So this is zero, this is zero, and this Z is very small. So this current is very high. Did you understand? Did you understand that there is some voltage and this Z may be in is a very small value. So this inrush current is very high and it can be so high that it can damage these diodes. The diode current rating may be smaller than this current, and if the diodes get damaged, then your circuit will not work, right? That's why it is necessary to limit this inrush current that flows initially. And once it reaches steady state, then it is okay. Then there is no problem because then the current is not this high. Because that time there will be some voltage across the capacitor. See, this quantity will not be zero in steady state. There will be some voltage. So the current will not be this high, like the initial instant when you are closing this switch. Okay. We shall see what are the different kinds of protection circuits that we use. So the simplest kind of protection, what do you think? What could be the simplest component that we can add here so that my current can be limited?
And resistor.
Yeah, resistor. That is the simplest thing that we can add to limit current in any circuit. That's what we will do. Yeah, another thing I forgot to mention. So before going to the protection circuits, here I have shown two cases. Where case one is when this switch closing instant is synchronized with the zero crossing of this voltage, source voltage. So when source voltage is zero, then you are closing this switch. So in that case, you can still limit the current somehow because then the capacitor voltage will start rising from zero. It will follow the source voltage and then it will reach this peak, and after that it will follow the steady state waveform, right? But if and this is like kind of a bit difficult to achieve, synchronizing the switch closing instant and the zero crossing. And the what is the worst case? The worst case could be when the your voltage is at its peak, then you are closing this switch. Then your this current, inrush current will be huge. It will be huge. Okay. A very peaky current of very high value. Why? because here Vi is maximum and there is no voltage across the capacitor. So it will draw a huge amount of current. So this is the worst case condition. And whenever you will design the protection circuit, you will have to take into account this condition. The method is whenever you will design anything, you will have to take the worst case condition and then you will have to choose the components and choose the choose different components and their ratings, right? If it can work in the worst case condition, then definitely it will work in other conditions. That is the theory. Okay. So these two cases are shown here when you start from this point and when you start at this peak point. Okay. So this current will be much higher than this current. This will also be a peaky current, but this current will be much higher than this one. Okay. So what we were discussing, the protection circuit. So resistive protection circuit is the most basic one. This is called surge limiting resistor. It limits the surge current. That's why it is called the surge limiting resistor. We connect this resistor in series with the source. Okay. So definitely whenever you will close this circuit, this resistor will limit the current value. Okay. And how will you select the value of this resistor? So the minimum value of the resistor should be this V peak max by I limit. What is the V peak max? V peak max is the peak value of the source taking into account the range. Like in the last question, I showed you some range of the grid voltage. So if 230 is the nominal value, it will not always stay at 230 volt. It can go beyond 230 volt and it can also come down from 230 volt. So whatever will be the maximum limit of this voltage and the peak it and corresponding to that value, you will have some peak voltage. That value you should consider, that peak value of voltage. And this current is what is the limiting current? The current will be the non-repetitive peak current of the diode. So these diodes, in the diode datasheet, you will see a parameter which is called the non-repetitive peak current. Okay. So this is non-repetitive means it can't withstand this current multiple times. It can withstand that current once. So that's why it is non-repetitive. So this is the surge current rating of the diode. And if you just if you will have to see this value and you will have to put it here. Whatever will be the whatever resistance you will get, that is the minimum resistance. So you should choose a value greater than this for safety. You will have to choose a resistance value which is greater than this. So that's how you can choose this surge limiting resistor. Now there are some pros and cons. Pros and cons. So pros, which the advantage is very obvious that this is the simplest solution. You will just have you just need one resistor. That's it. That is the most. This is the most simple solution that you can get. And what is the con? Con is that this is a lossy solution because once this circuit reaches steady state, you don't need this resistor. You only need this resistor during starting period. So this resistor will keep on like whenever the current will flow through this resistor, there will be some loss and some voltage drop will occur across this resistor. So at these points you will get a voltage which is lesser than this voltage. So your output voltage will also be lesser due to the drop across this resistance. So these are the disadvantages of this solution. Okay. So there are some other solutions also to so that we don't have to so that we can reduce this loss. Okay. So what are the this is solution first solution. The second solution is thermistor. So what is a thermistor? Thermistor is a resistor whose value changes with temperature. Here I have shown a graph of a thermistor. It is also called NTC. NTC means negative temperature coefficient. So as the x-axis is temperature and y-axis is the resistance value in log scale. So here you can see as temperature increases, the resistance value decreases. That's why it is called negative temperature coefficient. What is the advantage? What advantage it will give us? So initially, when you are starting the circuit, so that time temperature is very small, right? So suppose 25 is the ambient temperature. So that time you have this high resistance of this thermistor. So it will restrict the inrush current. It will limit the inrush current, right? Now it has done its job. Afterwards, when the circuit goes into steady state and current starts flowing, so eventually the temperature of the resistance rises, obviously, because there is some loss. As the temperature rises, its resistance will fall. As the temperature rises, its resistance will fall, and it will be a smaller value. So that's why your loss will reduce, because now the resistance value is smaller compared to the initial time. As the resistance value falls, then you will have lesser reduced loss due to this resistance, right? That is the advantage. But there is one concern. The concern is, if suppose there is some fault and your this switch and your power goes out, okay, so that time your the power is gone, so now there is no current, right? But then after some time, if the power again comes back, but then the resistance value has not regained this initial value, it has not reached the initial value, the resistance is still smaller, then it can't limit the current, right? Because its resistance has not yet regained its initial value. Suppose it is here, it was here, from this point it has come to this point, but not at this point. So that's why like this is the problem, that if there is power cut and then again power comes back here, so that time the resistance value is not sufficient to limit the current to a safe value. That may be a problem here. Clear? And here I have written the part number of the thermistor which I have taken the graph from. You can search this part number and check the different parameters of a thermistor. This is solution number 2 for limiting the inrush current. Let's see what is the third solution. The third solution is using a transformer. So after this source, we will have a transformer which has a turns ratio 1 is to 10, 1 is to n. And after this, with the secondary of this transformer, we have the diode bridge rectifier and capacitive filter and the load. So the first advantage is very obvious. There is no loss because transformer is a passive element. And so there is no loss in the transformer. In an ideal transformer, practically there will be some loss, but that will be very negligible, very small. So this is not a lossy solution. Unlike the resistance one, there will be no loss. Another advantage is galvanic isolation. What is galvanic isolation? So whenever you are using a transformer, so this primary and secondary, they are physically isolated. So this point and this point, they are physically isolated. So if there is some surge or some kind of fault here, that will not be reflected here. So your components are safe. And also if there is some surge or something in this side, then that will not get reflected in this side. That is the advantage of galvanic isolation, because these 2 points are physically isolated. They are not there is no electrical connection between this point and this point, right? Another advantage is that as they if you just choose the turns ratio properly, you can get voltage according to your wish. You will just have to choose. You have this flexibility of choosing the voltage here based on this turns ratio. Suppose you don't want 230 volt, you want a voltage lesser than 230 volt, so you can choose the turns ratio accordingly, so that you will get a reduced voltage here, and afterwards you can just rectify it and get the voltage according to your desire. Okay. And there is also you can also choose a higher turns ratio, so that you can get a voltage higher than 230 volt in these two terminals. So that is also possible. You can have a step up transformer, you can also have a step down transformer. That is another advantage. And also it limits the inrush current. How it limits the inrush current, that we will see. So these are the advantages. And the disadvantages, as you place a line frequency transformer here, the system gets bulky, because the size is bigger. The transformer takes a substantial amount of space, and it also adds to the cost of the system. So that is the disadvantage. Okay. uh, let's see how the transformer limits the inrush current. So here, whatever you are seeing here, this is the equivalent circuit, equivalent T model of a transformer. So this is the primary winding resistance. This is the leakage inductance of the primary. Then there is this mutual inductance. Again, the secondary side leakage and the secondary winding resistance. Usually this mutual inductance is very high, so the current passing through this path will be negligible, very small. So you just so all these things comes in series. If you just neglect this current path, we can assume that there is negligible amount of current passing through this due to its large value. So all these RP, LP, LS and RS, they come in series. So all these components basically limits the inrush current. There is resistance also, there is inductance also. And the current will be what? The current will be L. So the voltage, we know voltage is what? L di by dt. So based on this leakage reactance value, your current will build up in the circuit. Okay. So they will limit the inrush current. So this solution is a good solution. Other than that, it is a bulky solution and it adds to the cost. Other than that, it has many advantages. Okay. This is the third solution. Let's see the next solution. So solution number 4 is using active devices. Active devices means where we can control the turn on and turn off. So active device, here MOSFET has been used. How this circuit works. So here you see that this voltage, this rectified voltage, there are two resistors. So this is a resistive divider circuit, and from this midpoint, this point is going to the gate terminal of the MOSFET, and there is a capacitor in parallel with this resistor, right? So what is happening here? Initially, our only concern is initially we need to restrict the inrush current. Afterwards, like when it reaches the steady state, it is okay. There is no problem. Only in the initial phase, we need to restrict the current. initially when you are closing the switch, there is no voltage across the capacitor here, and there is no voltage here, right? So just after in the suppose in the first cycle, uh, there is some voltage comes here after rectification, and so if there is some small amount of voltage, so due to this resistive divider circuit, some voltage will come here and some voltage will be given to the gate circuit. So the gate voltage, the gate to source voltage starts rising like this. So initially the voltage is very small, and gradually this voltage increases. As this voltage increases, the voltage across this capacitor also increases, right? And the this the resistance of this MOSFET, it has a relationship with gate to source voltage like this. So this is the portion when this is suppose the threshold voltage of the MOSFET. So initially the voltage rises to threshold voltage. That time RDS on is very high. Afterwards it goes on rising, and the resistance gradually falls. And when it reaches suppose exceeds 12 volt, so the resistance becomes very small. So the idea is, during the initial phase we are adding one resistance. This kind of acts as a variable resistance. Initially this resistance is high. Initially this resistance is high, and as time passes this resistance decreases. And by this time the circuit reaches steady state. So now we don't need a high value of resistance. So now this MOSFET is fully on and the circuit operates in steady state. Okay. So that's what it does. Initially, it offers a high resistance to limit the inrush current, and as it after some time the resistance decreases because now we don't need any resistance in the circuit because now it has reached the steady state. The current is small, so now we don't need any resistance. That is the yeah, working principle of this solution. Okay,
And
clear?
in the graph,
Yeah.
these these 2 volt, 12 volt, and 15 volt values, what are these? Are these fixed?
No, they are not fixed. These are some sample values. Usually we give 15 volt and minus 5 volt, but these may be other values as well. This is just written because to understand a bit in a better way. These values may differ from device to device. It may be 20 volt, this 15 volt may be 20 volt also, or lesser than 15 volt as well. And this threshold value is also different for different devices. I have just written just for giving an example, that's it. They are not fixed values. Okay. So yeah, but there is one problem in this circuit. What is the problem? That just we studied MOSFET. When we studied MOSFET, we saw that there is a body diode in the MOSFET. There is an inherent PN junction in the MOSFET. So the problem is, suppose when the same problem, suppose the power is now off, some fault or something came, so now the power is gone. So the capacitor will discharge through which path? This filter capacitor, this will discharge through, it can discharge through this path, through this body diode. So when the power comes back, then at that time, uh, the because this capacitor is discharging and in the process it is charging this capacitor, so this capacitor is already charged. So again when the power comes back, that time it can't restrict the inrush current, because at that time the VGS voltage is already high, and that's why the RDS is very low. So that time it will not restrict the current, because this capacitor is discharging through this path, through this body diode. That's why instead of making the circuit like this, the circuit is made in this way. So another two diodes are here, and they also act as full bridge rectifier, and the resistances are connected like this. So now they can't discharge, the capacitor can't discharge through this body diode. So this is a modified version of this previous circuit. Okay, so that if in between the power goes off and after when power comes back, it can again offer higher resistance during the initial phase, and then the resistance goes low. Okay, this is the fourth solution. The fifth solution and the last solution is using relays and contactors. So what is contactor, what is relay? This is the total circuit. This thing here, this is a contactor. There will be these two terminals and there will be this contactor. Whenever this contactor comes down, the circuit is complete, and whenever it goes up, the circuit is open. Okay, and this is the coil. This is a coil, and across this coil you can see this coil is connected across this supply. So this is tapped here. This terminal is connected here, and this terminal is connected here. There is one switch as well. When the switch is closed, the total grid voltage will appear across this coil. And if the coil is energized, this is a solenoid kind of coil. So whenever this coil is energized, there will be there will be some magnetic attraction, and it will pull this contactor, and the contactor will be uh, the contactor will come down and it will complete the circuit. And when it is de-energized, it will go up and the circuit will be open. That is the operating principle. And here it is the relay. Okay, this is the relay. So you can see there is another coil and there is this BJT. There some DC voltage is applied here. So if the DC some current, whenever the BJT is on, some current will flow and this coil will get energized and it will, and the switch will be closed. They are coupled. This switch and this relay coil, they are coupled. So whenever current flows through this coil, the switch will be closed and it will in turn energize this coil, and the circuit will be closed by this contactor. And whenever this BJT is open, there will be no current through this coil. This switch will be open, and this circuit will also be open because now it will not attract this contactor. Okay. And the relay coil, how it works? So this
Is what is this green
what?
about the contactor?
Sorry.
About the contactor, there is a connection of a green in green color. What is that?
Yeah, right. I will tell what is that. So basically, this is a resistance. Okay, this is a resistance. So initially, what was the first solution we saw? That was connecting a resistance. So first, when this circuit is closed by this switch, this contactor will be open. The current will flow through this circuit, and as this resistance is there, the inrush current will be limited. Now, when the circuit reaches steady state, that time we don't need this resistance. that time this contactor will be closed and it will bypass this resistance, because now we don't need this. The job is already done. We have limited the inrush current during turn on. Now we don't need this. So why should we have some loss in the resistance? There is no necessity. So that's why we will bypass this resistance through this contactor. Okay, that is the point. This resistance, the current will flow through this resistance only when this will be closed for the first time during the initial phase. Afterwards, this path, there will be no current through this path. The current will flow through this contactor. So if you see this output voltage we are tapping, so there is again a resistive divider circuit, and from this resistive divider circuit, like we are attenuating this voltage, and this voltage we are tapping here at the positive terminal of the op amp, and the negative terminal is connected to a threshold voltage. Suppose some any, it can be any voltage, some predefined voltage. So as the voltage starts rising, this output voltage, this voltage will also rise, and after some time this voltage will become equal to this threshold voltage, and that time the output of the op amp will be high, and it will provide some base current to the BJT. And whenever it will provide the base current to the BJT, this path will be complete, the BJT will be closed, so the current will flow through this BJT, and then this circuit will again be closed because they are coupled. So this switch is closed. Now this coil gets energized now, because some voltage appears across this, the supply voltage appears across this coil, and it will pull the contactor. Now as the contactor is pulled, this resistor gets bypassed, and now current will flow through this path. It will not flow through this path. The current will flow through this path. So after when there is some voltage already built up in the capacitor, across this capacitor, then only this contactor will get pulled. That is the operating principle. Okay, whenever there is no voltage, so there will be no voltage in the positive terminal, and the op amp will be low, like there will be no output from the op amp. That's why this BJT will not get any base current, because this is low, there will be no base current, and so this is not energized, this switch is open, and this is also de-energized, so the contactor will be open, it will not be closed. Only when some voltage appears here, and then only some voltage will appear here as well, and unless it gets equal or greater than this threshold voltage, the op amp will not get high. That is the point here. Okay, so this is the most robust solution among all these solutions that I told you. This is the most reliable, most robust solution. Okay, so did you understand how this is working?
Ma'am, is it complex?
Yeah, it is a bit complex, so I will suggest you just you go to the lecture and listen to it once in the, like Umanand sir's lecture you listen, and this will also be uploaded. You listen to it and you try to understand how it is operating. If you don't understand, in the next session I can again explain. Okay, you just remind me once, I shall explain it once more. So let's proceed. So this is a three-phase uncontrolled rectifier. Earlier we saw the single phase rectifier where there was the single phase grid, single phase AC supply. Now there is three-phase AC supply in the input, and there are three half bridges. This is first half bridge, this is the second half bridge, and this is the third half bridge. And we have the load here. Okay. So here you will get a output voltage, you will get a output voltage envelope like this. In the absence of the capacitive filter. When there is no capacitive filter, you will get a 6 pulse output voltage like this. Why this is called 6 pulse? Because there are, if you observe, there are 6 humps like this, 1, 2, 3, 4, 5, and this becomes the sixth one. So there are 6 humps. So this is called 6 pulse output voltage. In 3-phase diode bridge rectifier, you get this kind of voltage. So it operates in the same principle as the single phase rectifier. So this is the common cathode configuration, the top diodes, and the bottom diodes are in common anode configuration. And there are 3-phase supply here. So whichever diode, whichever diode is getting the most positive voltage, that diode will get forward biased. And for the bottom diodes, whichever diode, which anode is having the most negative voltage, that will get forward biased. Okay. So at a time, any two diagonal diodes will conduct. Okay. And you will get this kind of voltage. So I will explain this more afterwards. So this is a 3-phase rectifier. The operating principle is same as single phase rectifier. There is no difference. Just that you have 3 legs instead of 2 legs. And here the voltage fluctuation is lesser than the single phase one. In single phase one, in the absence of filter, we saw the voltage is something like this. It has a sinusoidal template, and it reaches zero at each half cycle, right? It was something like this we saw already. So the voltage would be something like this. So from zero it will start, it will again come to zero at pi, and this cycle repeats. But here if you see, the fluctuation is lesser. In the absence of filter also, the this difference between this point and this point, this is much lesser than the single phase rectifier. Okay. So now we shall start the problems. So now the time is 7:09. I shall take a small break of 4 minutes. Then I shall start the problems. Okay. In the meantime, if you have any question, you can ask me after this 4 minute break. You just you can just see the you can yeah. If you have any question, just ask me. Uh, anyone have any question? Whatever we discussed so far. So,
The chat section is off.
what?
The chat feature is not working. It is off.
Acha, you are not able to send any message here?
Yes, ma'am.
Acha, okay, okay, I will see.
Maybe it's a
So,
problem from my side.
so you have any question or any doubt? So I guess this one you found a bit complicated, right? This solution. So I shall explain it once more. But still, if you have any doubt, you see Sir's lecture. And still, if you don't understand, you can ask me. In the next lecture I shall explain again. So what is our objective? Our objective is to limit this inrush current. When we will start this circuit, we want that the current shouldn't be very high so that these devices gets damaged. We want to reduce this current. Okay. So what was the most simple solution? To add a resistance in the circuit in series with the source. That's what we have done. We have added one resistance. But the problem is, after this initial phase is over and the circuit goes into steady state, this resistance is not required anymore. But if we have this resistance here, it will the desire and it will go on making loss, which is completely unnecessary. Now we don't need this resistor, but the resistance is present and it will make some loss. So how we can avoid that? To avoid that, what we have done, we have created one parallel path through this contactor. So if the contactor is closed, the current will not flow through this resistor. The current will flow through this path. Because the contactor, this resistance is nothing compared to this resistance. This is a very small resistance, almost negligible. So current will flow through this path, not through this resistance. How we can ensure that after some time this contactor will be closed, not in the not initially. That's why we have connected all this circuitry. All this thing is just to make sure that this contactor is pulled after some time when the initial phase is over. So initially there is no voltage across the capacitor. That's when we want to restrict the current. So that time the contactor is open, current flows through this path and it is limited. Now as the capacitor gets charged, voltage will start building across this capacitor. As voltage starts building across this capacitor, there is this resistive divider circuit. So you will get some voltage across this point as well, across this resistor as well. And this point is connected where? To the positive terminal of this op amp. And in the negative terminal of the op amp, we have already given some threshold voltage. Okay, that value you don't need to think upon now. Suppose there is some threshold voltage, some 8 volts, some 6 volts, something like this, and some voltage is coming from this point as well. When the op amp will get output will be high. When the positive terminal voltage is greater than or equal to this negative terminal voltage, right? That's when the op amp will give high output. And when this op amp gives high output, then some base current will flow through this BJT. And when base current flows through to the BJT, the BJT will turn on. And there is some DC source here as well. There is some DC source here also. Suppose there is some, this is a DC source VCC. Okay, some DC value. So when this BJT is on, the current can flow through this coil from this point to this point. Now, as current flows through this switch and this coil, they are coupled. So this switch will be closed whenever this coil gets energized. As this switch is closed, this 230 volt, this input supply comes across this coil, because the coil, this point is connected here and this point is connected to this point. So this 230 volt appears here and this coil is energized. It will pull the plunger. It will pull this downwards and the circuit will be complete. Okay. But this happens only when there is some voltage already builded here. Otherwise, this op amp will not be high. This output of the op amp will be low unless some certain amount of voltage comes here which is greater than this threshold voltage. That means the circuit has already reached steady state. Whenever some voltage already built up here, the circuit has entered steady state. Now there is no point of this resistance. Now we can bypass this resistance and current should flow through this path instead of flowing through this resistance. That is the point of this relay and contactor. Okay. So this is the circuit. So if you still have doubt, we can discuss it in the next session. Today we will not get time. So let's start the problems. The first problem is, consider a capacitor filter full bridge rectifier which uses a resistor based inrush current limiting. The resistor has a nominal value of RS with tolerance of plus minus 10%. Supply voltage is 230 volt. It also has a range plus minus 20%. Calculate the minimum value of RS if the diode used is this. So you need to refer to the datasheet of 1N4007 for calculating the value of RS. What is the solution? So this is the resistance based solution we saw as the first solution to limit the inrush current. So here, what is the first task? Sorry. So the first task is to calculate the maximum peak value of the source voltage. So the range is 20%. That's why 1.2 into 230 root 2, which gives us 390 volt. And the minimum value of surge limiting resistor will be 0.9 RS. Why 0.9? Because it also has a range of plus minus 10%. So the minimum resistance should be able to limit the inrush current to a safe value. Now, if you just refer to the datasheet of one in this diode, so you will see the non-repetitive peak surge current rating is 30 ampere. So we already saw that your resistance value should be greater than Vs max by Is max. What is Vs max? We already calculated 390 volt. Is max is 30 ampere. So Rs minimum should be greater than 13 ohm. And Rs minimum is 0.9 Rs. So Rs is this by 0.9, which is 14.45 ohm. So the minimum value of nominal resistor will be 14.45 ohm. That's how you will have to calculate the surge limiting resistor value. This is your current limit. So when whatever resistance should be here, this should limit the current lower than this value, because this is the limiting value that the diode can withstand. The resistance should limit the current within this value lesser than 30 ampere. So if we use a resistance more than 14.45 ohm, we will be able to limit the current below 30 ampere. And here we have taken 0.9 RS because they have given that we have a tolerance of the resistance which is plus minus 10%. And if our nominal value is RS, the resistance value can sometimes go below RS. So it will go, and what is that amount? That is 10%. So if it goes like if it is reduced by 10%, the value will be 0.9 RS. That's why I have taken 0.9 RS. This is the worst case condition. So your resistance value is the minimum and your V is maximum 390. In that portion, your current should be limited within 30 ampere. If in this portion you can limit the current, then in all other conditions it will be limited within 30 ampere. That is ensured. Fine. Let's go to the next problem. The next problem is calculate the loss associated with the resistor in question 1. If the peak value of the input current is 10 ampere and the conduction angle alpha is 22.6 degree, assume the current to be a square waveform during the conduction period and use nominal value of resistance. So this is related to question 1. Additional data are given. The maximum input current is 10 ampere. All this data, like this is for steady state. Okay, this is for steady state. Alpha is 22.6 degree. What is alpha? This is the charging duration. When the capacitor gets charged from this point to this point, this is the angle alpha. Like earlier, we also denoted it as beta. Sometimes they denote it as alpha also. This is the angle alpha. And they are telling us this current shape is not square actually. This is a peaky sort of current. But they are saying you can assume it as a square wave. So they are saying like this you can assume as a square waveform instead of this for the ease of calculation. Okay. We need to find the loss in the resistor. In this, so in this resistor, we need to find what is the loss. So we have assumed square current. This is the current and this is the alpha duration, and maximum this value is 10. This peak is 10 and this is the input current. So we can find out the RMS value of the input current, which will be, this is the 10 multiplied by root over alpha by pi, because alpha is the duration when we have current and the total duration is pi. In the negative half cycle, we also have current and this is symmetric. So that's why we have taken pi duration, because they are symmetric. Into like instead of taking 2 pi, we have taken pi. Okay. So 10, this is the RMS current that flows through the resistance. So what is the loss in the resistance? I RMS square RS, right? So current square times the nominal value we already calculated earlier. This was the nominal value. So this is the loss in the resistor. So you see there is a significant loss in the resistor and this is not required. We just need the resistor during the initial period, but afterwards if it is there, we will have to incur this amount of loss. That is the disadvantage of the resistance solution. This is lossy and it reduces the efficiency of the circuit. Fine.
Ma'am, how alpha by pi?
because because this is a quasi square wave, right? If you just calculate the average, you can calculate it in the conventional way. How we calculate? We calculate the average value in this way. So you have integral this I dt, or suppose you can also write d omega t if it is omega t is the x-axis, then you can write it in terms of suppose this is I and this is d omega t, and here you have 1 by 2 pi. 2 pi is the total duration, but we are not taking 2 pi, we are taking pi because this current and this current, they are same. Just it is positive, it is negative, but they are same. So we can take pi also. Okay. We can take the duration, total duration as pi, and this is 0 to pi. Now, the current only exists during this, only in this duration, only in the alpha duration. Rest of the time, the current is 0. So what will be the average value? It is 1 by pi, and this is 1 by pi here. This is the, suppose this angle is some alpha 1, and this angle is alpha 2. Okay. So from alpha 1 to alpha 2, you have current. What is the current? We have assumed a square wave, so I value is 10. This is during this duration, you have a constant 10 ampere current. So 10 times d omega t. So 10 goes out because this is a constant. So we have 10 by pi, and omega t, if you just integrate it, it will come out to be alpha 2 minus alpha 1. Alpha 2 minus alpha 1, which is nothing but alpha. Right? This is alpha, right? Alpha 2 minus alpha 1, this is alpha. So your average current will be 10 into alpha by pi. And if you calculate RMS current, you will get a root over here, because RMS current is what? Root over of, again, 1 by pi. You can compute it by yourself. So it will be 1 by pi. It will be 0 to pi. So instead of I, it will be I square times d omega t. If you compute this, you will get this root alpha by pi. Okay. You can calculate it by yourself. You will see. So that's why I have written the RMS value is 10 times alpha by pi, root over alpha by pi. Okay. So I square will be, this will be 100. So if it comes out from the square root, it will be 10. So 10 comes out, and here 1 by pi, it will be alpha 2 minus alpha 1. So alpha by pi under a square root. So this comes out to be this one. So once we have the RMS current, the loss is simple. I RMS square times RS. We have the values. So this we calculated in the first problem. This is the loss in the resistance. Next problem. What is the next problem? For question 1, if the forward voltage drop of the diodes is 0.5 volt and the output voltage ripple is 25 volt, calculate the efficiency of the rectifier system Use nominal values of all parameters and ignore tolerance. So now earlier they didn't mention, but now they are mentioning that there is a forward voltage drop in each diode. In all four diodes, there is forward voltage drop of 0.5 volt, and they have also mentioned a ripple voltage of 25 volt. So what will be the efficiency of the rectifier system? What we need to do is first we need to identify where where we will incur some loss. Okay, we already saw there will be some loss in this resistor that we calculated also. Where else? There will be some loss in all these diodes, right? Because a forward voltage drop is there, so some loss will be there in the diodes. We need to calculate these losses. So we calculated the loss is we this one we already calculated in the last problem. Now we need to calculate the average current through the diode, which is alpha by 2 pi. Why this is 2 pi? Because each diode conducts only once in a 2 pi duration. In the positive half cycle, this diode and this diode will conduct, and in the negative half cycle, this diode and this diode will conduct. So each diode conducts only during this duration in a total 2 pi duration. That's why now this is alpha by 2 pi. And this is the current 10 ampere IM. This is 10 ampere. So ID average is this value. And they have mentioned the forward voltage drop as 0.5 volt. This is 0.5 volt they have given. So 4 times, because there are 4 diodes. So 4 times VD times ID average, this comes out to be 1.25 watt. The total loss in the circuit is summation of this loss and this loss, which is 182 watt. Okay. Now what next? Now they have told to use the nominal values. So now we have our peak value of the so our peak value of the output voltage is nothing but the peak of the phase voltage. So 230 root 2 325, and the minimum value is maximum minus the ripple voltage, which is already provided 25 volt. This is 300 volts. So average output voltage is Vmax plus Vmin by 2. We saw, right, that this is the output voltage shape, something like this. So uh, suppose this like this, it somewhat like this. So this is the ripple, the difference of maximum value and minimum value. And this maximum value is the peak of the phase voltage, and minimum value is maximum minus ripple. And the average of these two values gives us the average output value, voltage. And average value of the output current is Im times alpha by pi. Why? Because I am talking about this current. I am talking about the current that enters here. Okay. So this is the current, this current I. So you see, if we assume this is a square wave, then again this value is nothing but the average value is 10 into alpha by pi, right? That we already saw. That how this average current is coming. Alpha by pi. So this is this current. This current. So if we have the average current, and we have already calculated the voltage, the output power is voltage and current multiplication of voltage and current, 391 watt, and the efficiency is output power by output power plus loss. So this is the input power, loss plus output power, and this is 68.2%. This is the efficiency of the system. Fine.
Ma'am, in the circuit the tolerance means?
Tolerance means the range. If there is some tolerance given, that means if plus minus 10% in the tolerance, that means from the nominal value it can go to like it can be 10% higher than the nominal value, and it can go beyond it can go like 10% lower than the nominal value. Uh, that means the tolerance. Okay. So if suppose your nominal value is 100 volt, so plus minus 10% tolerance means this is the nominal value, but it can go to 110 volt also, and it can also go to 90 volt. So 90 volt to 110 volt will be the range, and this will be the nominal value. That is the meaning of tolerance. Okay. Hmm. Huh. So next question. Increasing the value of filter capacitor in the full bridge rectifier leads to. This one, you try to answer it. What will be the correct option? If we increase this filter capacitor value, if we increase this value, if we increase this capacitance value, what is the consequence?
Now input current will be increased.
Input current will increase, okay? And what is the other effect? Increase in input current is in the two options, in B and in D. And there is another thing. What will be the effect on voltage ripple? So if we increase the capacitance value, the voltage ripple decreases. As you increase the capacitance value, so if this is for C1, suppose, if this is suppose for C1, and if this is the output voltage, suppose V0, and if this is the output voltage for C2, then this is also V0. This is for C1, this is for C2, then C2 is greater than C1. As you increase the capacitance value, your voltage ripple will decrease. Okay, so option B is the correct option. Next question. Calculate the value of the inductor in the circuit such that the power factor of the network is unity. So while discussing this week's contents, I didn't discuss about power factor. Do you guys know what is power factor?
And power delivered to load divided by input.
No, not exactly. So basically, power factor is a measure of like how close is your load to resistive load. Power factor is a quantity. So power factor basically varies from 0 to 1. Its magnitude varies from 0 to 1. It can be leading also, it can be lagging also. So power factor is a measure. So power factor is 1 when your load is purely resistive. But if there is inductive load or capacitive load, it will differ from 1. It will not be unity power factor. So how close is your circuit to a pure resistive circuit? That we can tell from the power factor. Okay. So if this is the AC supply and there is some components are there, some resistance, inductance, capacitance, they are there. So if it is not a resistive, it doesn't, if it offers a pure resistive impedance, so if your Z is some resistance R, then only if this is your supply voltage, the current will be exactly in phase with the supply voltage, and it will be something like this for a pure resistive load. But if it is a inductive load, suppose a mixture of resistance and inductance, then this is your supply voltage. Suppose this is the supply voltage. This is Vs, Vs, and this is Is, your current, supply current. Okay, this is supply current. If this is an inductive load, then your current will lag the voltage. Lag means the current zero crossing will be later than the voltage zero crossing. Okay. So this is the current zero crossing. This happens after some time from the voltage zero crossing. This is for inductive load RL. So now in this case the power factor is 1 because the voltage and current they are in phase. But here the power factor will not be 1, it will be less than 1 because now they are not in phase. The current is lagging the voltage. And for RC circuit it is the opposite. Now the current will lead the voltage. The current zero crossing will happen earlier than the voltage zero crossing. Okay. So that is the case for RC type of load. For purely inductive load, the current will be exactly 90-degree lagging the voltage. For pure capacitive load, the current will be leading the voltage exactly by 90-degree. And if it is a mixture of resistance and inductance, resistance and capacitance, then it will be something like this. Okay. So this is called the power factor. If I get time, I will discuss elaborately. But I don't think today we will get time. Anyway, next class we can discuss again. So they have asked if this is the circuit, what value of inductor will ensure that this is the power factor is unity. Okay. If you see here, just by intuition, you can say this is resistance, all these components are resistances. The only reactive components are this inductor and this capacitor. So if we can ensure this inductive reactance and the capacitive reactance, they are of equal value, then the circuit will be purely resistive because all these are already resistances. Only these two are the inductive and capacitive elements. So the solution is very simple here. How we define capacitive reactance? 1 by omega c. This reactance is at a particular frequency, and the frequency here is the supply frequency, which is given 50 hertz. So at 50, this capacitive impedance is 1 by omega c, and the inductive impedance is omega l. So if we can ensure xl is equal to xc, then there will be no react impedance here because they will cancel each other. This is the inductive reactance and the capacitive reactance. They will cancel each other, and the whole impedance will be purely resistive. The effective impedance that is seen by the source, that will become purely resistive, and the power factor will be unity. So I have simply just equated them, and from here we can get the L value, which is 1 by omega square C. Okay, what is omega here? Omega is 2 pi f. 2 pi f. where F is the supply frequency, 50 Hertz. This is 50 Hertz. Okay. So that's how we can calculate the inductor value. Let's see the next question. A load voltage is of the form of this. This is the load voltage expression in terms of time, and the load current is 10 cos omega t. Calculate the power factor. So this is very simple. This is a cosine wave. This is also a cosine wave, but here it is omega t minus 30 degree, but here it is simply omega t. Clearly you can see that there is a 30-degree phase difference between the voltage and the current is leading the voltage. Why? Because the voltage phase is omega t minus 30, but the current is simply omega t. So the current is leading here. The power factor, we define the power factor as cos phi, where phi is the phase difference. So here the power factor is cos 30 degree, which comes out 0.866. It is leading. Why? Because now the current is leading the voltage. This is the voltage and this is the current. Because, right, so that's why it is leading power factor. So definitely the load is RC type of load. Why? Because when we have RC type of load, then only the current leads the voltage. If it if it is an inductive kind of load, the current will lag the voltage. The current zero crossing will be after the voltage zero crossing. Okay. So yeah. Is it fine? Okay. Next question is calculate the active power drawn by the load in question 6. So the same question, what is the active power drawn by the load? So active power is calculated by Vrms Irms cos phi, where phi is the phase difference. So Vrms we can calculate, the peak value is 325. So 325 by root 2, 230 volt. I peak value is 10 ampere. So this is also 10 by root 2. This is 7.07. Sorry, this is ampere. This is ampere. So the active power drawn by the load is Vrms Irms times cos phi. That is 1.4 kilowatt. So determine the type of load in question 6. Just a second. So we already saw that it was a RC type of load. Otherwise, the current wouldn't lead the voltage. The current here was leading the voltage. So definitely it is RC type of load. And it is not purely capacitive type. Why? Because the lead angle was less than 90 degree. If it was a purely capacitive load, then the lead angle will be exactly 90 degree, but it was 30 degree. So that's why it is a RC load. Okay. So this is a relay question, the protection relay circuit that we saw. A relay coil is used to limit the inrush current in a full bridge rectifier and is controlled using the circuit shown in the figure. Calculate the value of resistance if the relay coil must be activated at 1 second after the switch S is turned on. Just wait a minute, I shall connect the charger of my laptop. Just wait a minute. What they are asking? They are asking that this is a relay circuit that is being used to limit the inrush current in a full bridge rectifier. They have asked to calculate the resistance value so that after you close this switch is after after you close this switch after 1 second, uh, uh, the coil must be activated after 1 second. So the output of the op amp is going to the relay coil as I already showed. There will be one op amp circuit. So the output of the op amp should be high after 1 second of this switch has been turned on. That is the condition. That means the voltage at this positive terminal, this should reach 8 volt after 1 second of this switch is closed. Okay, that is the meaning. Because only when this positive terminal voltage becomes equal to this negative terminal, after that only we will get a high output from the op amp. So let's see. This is a bit you need to have a knowledge of RC circuit, okay, for solving this question actually. So when this switch is closed, we get a RC circuit where a step voltage has been given. This is the supply voltage. So the equivalent circuit becomes there will be one resistance and there is this capacitance. And here suddenly you are closing this switch. So suddenly this 15 volt appears here. So this acts as a step voltage. This is a step voltage of 15 volt you are applying here. Okay. So whenever there is a step voltage in a RC circuit, the governing equation is this one. This is the governing equation. Okay. This is the exponential. This is a exponential form. Okay. The voltage actually rises. If you plot the voltage across this capacitor, if you plot this voltage, the voltage will rise in a exponential fashion. And at steady state, it will reach this 15 volt value. Okay. When it reaches the steady state, it will attain 15 volt. So this is the equation, and this voltage is going to the positive terminal. That's why I have written this V plus, and this is V input. Okay. And RC, this is called the time constant of the circuit, which is RC. This is called the time constant. So we know this value is 15 volt, and this value we need to reach 8 volt. Because this is 8 volt, the threshold is 8 volt. When this terminal also reaches 8 volt, then this output will become high and it will energize the relay coil. And this should reach 8 volt after 1 second of this switch has been closed. Because there is a R, it will take some time to build the voltage, right? Because it is charging through this resistor. So here I have put 15. This is T by RC, this is 8. And this time is T is here, T is 1 second. Okay, that is given. T is 1 second. If you put all this value and solve this equation, you will get R value is 131.2 kilo ohm. Okay, and C value is given 10 micro. So you need R value which is 131.2 kilo ohm. Okay, and I think we have the last question. Which of the inrush current limiting technique is the most robust? That we already discussed that among all the solutions, the relay based technique is the most robust technique and also very reliable. Okay, that is the most reliable, most robust technique among all the solutions. Fine. Is there any question? If you do not have any question, I shall end the session today. And if you didn't understand any of the numericals, we can discuss again in the next session. I shall stop recording now.